We are discussing the Dirac equation. Now, for interacting particles, what should we do? Interacting particles. So, the interaction with an electromagnetic field represented by A mu. So, this we had already discussed will change P to P mu plus charge of the particle times A mu, where charge of the particle is minus E, electron like particle, and this gives gamma mu P mu minus m psi for free particle that is changed to gamma mu P mu plus E gamma mu A mu minus m psi is equal to 0 for interacting particles. This involves the kinetic energy term or the total energy, the free particle term plus the interacting potential term in the operator. So, we have to we will first isolate the potential exactly what it is and then use the perturbation method to understand the transition amplitude and eventually the cross section. What did we do? Just to remind us, we are interested in isolating the potential of interaction. For that, let us first look at what we did in the case of Schrodinger equation. Okay, what we have in the case of Schrodinger equation, it is minus h cross square over 2 m del square psi plus v psi equal to E psi. I have not put h cross equal to 1 in this, just for clarity, but in the other equations I will not put this h cross square, I will just take them to be equal to 1. So, Dirac equation with interaction term is gamma mu P mu plus gamma mu E A mu minus m psi equal to 0. We will expand the first term gamma 0 E plus minus gamma dot P, then we have plus E gamma mu A mu minus m psi equal to 0. So, I will take E to one side just to compare it with the Schrodinger equation, multiply it by gamma 0, that will give you E psi equal to, take the rest of it to the right hand side, I will have a gamma 0 gamma dot P psi minus E gamma 0 gamma mu A mu psi plus m gamma 0 psi. This is the Dirac equation with interaction term. Comparing with the Schrodinger equation, first term is the kinetic energy term, second term is the potential. So, V, it should be positive the potential. So, V therefore is equal to minus E gamma 0 gamma mu a mu. So, that is the potential coming in the Dirac equation. Now, using perturbation theory, we have the transition amplitude T f I equal to minus I integral psi f dagger V psi I d for x, that is equal to minus I integral psi f dagger minus E gamma 0 gamma mu a mu psi I d for x. I will take the gamma 0 with psi f dagger, write it as psi bar. So, I have minus I integral minus E psi bar gamma mu psi a mu, so psi f psi I d for x. This is nothing but the j f I mu a mu d for x. So, the transition amplitude is exactly in the same form as we had earlier, with this j mu now defined in this fashion. Again, like in the earlier case, we consider interaction between two charged particles. Okay. So, the a mu is caused by some other charged particle. In that case, I have T f I is equal to minus I integral j mu of one particle interacting with the a mu, which is caused by another particle, but again we can take j 1 mu, j 2 mu and del square a mu is equal to j 2 mu. This is just to remind you, and that gives you a mu equal to minus 1 over q square j 2 mu. This is what we had earlier. So, we have here minus 1 over q square j 2 mu, or I could write T f I as minus I two contravariant currents j 1 mu minus I, there is no I, minus g mu nu over q square j 2 nu d for x, d for x. Now, let us look at each current j 1 mu. I can think about a particular situation. I have a incoming particle with momentum p a, outgoing, but after interaction goes as p b. In that case, minus E psi a, sorry, this is the final particle. So, psi b bar gamma mu psi a is what I have. So, when I have psi a written as u a e power minus I p a x, and similarly for psi b, and the bar conjugate will actually take u bar and exponential minus I plus I p a x. So, psi a bar is going to be u a bar e power plus I p a x. Keeping that in mind, we have minus e u b bar gamma mu u a and exponential minus I p a minus p b x. Similarly, for the second current, this is mu, the second current, let us consider P c and P d as the initial and final moment. In that case, I have minus E u d bar gamma nu u b, not u b, u c e power minus I p c minus p d x. Putting together, I have T f I. T f I equal to minus I integral minus E u b bar gamma mu u a e power minus I p a minus p b x. This is J 1 and J 2 is minus E u d bar gamma nu u c e power minus I p c minus p d x, and you have the propagator g mu nu over q square, where q square is now the momentum transfer, which is P a minus P b, which is also equal to P c minus P d. This is equal to minus I minus E u b bar gamma mu u a minus g mu nu over q square. So, let me write it slightly up. Q is equal to P a minus P b. Then again, from the other current, u d bar gamma nu u c into integral e power minus I p a plus p c, two of the initial momenta, minus p b minus p d, the final momenta, x d for x, and this integral is nothing but a delta function. So, we can write T f I as minus I 2 pi power 4 delta for P a plus P c, sum of the initial momenta, minus P b minus P d minus sum of the final momenta, into an invariant amplitude m is equal to minus E u b bar gamma mu u a, propagator factor g mu nu over P a minus P b square, okay, and minus E u d bar gamma nu u c. We will look at the cross section, how we can write the cross section in the next class.